Hello, welcome to the first homework of the machine learning. Let's open the file. I was like C1, V2. One, where is I'm looking for it? Yeah, I guess this one. These are the macros files. This is empty. Yeah, this is empty. These are examples of datas, and this is a linear regression. For the kernel, I'm just choosing the Python Anaconda. And in here, first of all, we are just running the cell, importing the numpy and matplotlib with the utils.python file. With this, we're just importing this one in here. I'm gonna run here now. And suppose you're the CEO of a restaurant franchise and considering different cities for opening a new outlet. You would like to expand your business to cities that may give your restaurant higher profits. The chain already has restaurants in various cities and you have data for profits and populations from the cities. For these cities, you have the city population. Can you use data to help to identify which cities may potentially give your business higher profits? And we're gonna loading the data set in here. The in here we're just loading data sets, the X train and Y train. It's in the load data file, but I'm not sure where is the load data. Could be in here or could be in here. Yeah, load data in here, and load data makes X train and U train in the utils. We're just data X data 1 and X data X data. We are just importing these things in here, and with the variables before starting any on task, it's useful to get more familiar with your dataset. A good place to start is to just print out each variable and see what it contains. The code below prints the X train and type of variable. Okay, we're just importing it. It has a 5 trains and 6.1, 5.5, 8.57 and 5.8. We can actually make the U train for it also. Yeah, let me run it. It didn't run actually. Yeah. Yeah, actually U train, but is this the same? Am I making mistakes? Yeah, print type of X-ray type R. Yeah, I have to change this one too. Sorry about it. Yeah, in the U train is 17.5, 9.1, 13.6, 11.8, and 6.8. I'm gonna change the values again. And let me run to look at this one. Okay. Oh, actually, it's here the U train. We already have done it actually. And numpy contains decimal values that are greater than 0 to represent the city population times 10k. For example, 6.1 means that population for this city is 61,000. And we're just running here the train. Similarly, utrain is a numpy array that has decimal values, some negatives, some positives. Actually, there are no negative I haven't seen, but we can check from here, I guess. Yeah, this is the x values. Oh my god, sorry. This is the x values, this is the u values. I'm remembering it from the here in 9.1. Yeah, left side is the x values, right side is the u values. Some negatives, it says negatives, but yeah, here negative, okay. They represent your restaurant's average month profit in each city in units of 10k. For example, 17.5 represent 1,750. Oh, sorry, 175k in average month profit for the city. And check the dimensions of variables. Okay, for the how much values in here, the shape of x is 97, u is 97, and training example is 97, as we can see here. Actually, this is comparing only the profit per city with the population with the city. The population array has 97 data points, and monthly average profit also has 97 data points. These are NumPy 1D arrays, one dimension arrays actually. And visualize your data. It is often useful to understand the data by visualization. For the dataset, you can use a scatter plot to visualize the data, since it only has two properties to plot: profit and population. Many other problems that you will encounter in real life have more than two properties. For example, population, average household income, month profits, month sales. When you have more than two properties, you can still use a scatter plot to see the relationship between each parent properties. And let's run in here. Uh, Sorry about the disruption. And in here we are seeing the uh, displaying the scatter plot, which is populations and profits with the x and u levels. We are visualization that one. And the goal is build a linear regression model to fit this data. It's like, okay, sorry about, will be like this one. And with this model you can then input a new city's population and have the model estimate your restaurant's potential monthly profits for this city, and okay, refresh on linear regression. In this practice lab, you will fit the linear regression parameters w and b to your dataset. The model function for linear regression, which is function that maps from x to u. X is which is the city population, and use your restaurant's month profit for each city represent at function wbx of x equal to w times x plus b. To train a linear regression model, you want to find the best WB parameters that fit your data set. To compare how choice of WB is better or worse than another choice, you can evaluate it with a cost function j of WB, and j is a function of WB, that is the value the cost of j WB depends on the value of V and B. The choice of W and B that fits your dataset best in the one that has smallest cost, JWB, to find the values W and B that gets the smallest possible cost, J of WB, and you can use a method called gradient descent. With each step of gradient descent, your parameters WB come closer to optimal values that will achieve the lower cost J of WB. The trained linear regression model can then take the input values x for city population and output a prediction function VB of x predicted month profit for a restaurant in that city. And in the part 5 we are just comparing. Okay, we was in the 5. Uh, isn't it? Yes, we are computing the cost. The gradient descent involves represents steps to adjust the value of parameter WB to gradually get a smaller and smaller cost J of VB, and each step of gradient descent it will be helpful for you to monitor your progress by computing the just J of VB as WB gets updated. In this section, you will implement a function of calculate J, V, and B so that you can check the progress of gradient descent implementation. The cost function is, as you may recall from the lecture, for one variable, the cost function linear regression, J of VB is defined as here. In this one, I'm not sure how I can read this one. And you can think of function VB x I. This is a model prediction of your reference process as opposed to E over I, which is a actual profit that's recorded in the data and is the number of training examples in the dataset. And model prediction for linear regression with one variable, the prediction of the model FVB, for example, X or E is represented as here, and this equation for a line with the intercept B and a slope of V. And for the implementation, complete the compute cost function below the complete the cost J of B, and in here the exercise one, the compute cost below to here actually the some mathematical function and summation method, and we can run it in here, the compute function. There are different x, u, v, and b. If you get stuck, you can check the hints represented after the cell below to help you with the implementation. Okay, let me run it. Click for the hints. Well, okay, what's in here? Okay, let me check it. Click for the hints. Okay, this is a hint actually. You can check the implementation was correct by running the following test code. Okay, let me run it. These are error because I haven't changed anything. These are the hints actually, and this is the args, and we haven't defined and the other stuff. I will stop recording in here to find that methodology, and then I'm gonna restart the recording after I done it. Yes, in here I haven't run actually, but I just defined the W, X, and B. For the predictions, we are here. I'm just at it for this one, and we are just minus U and square root for this part. Then we are just adding the 1 divided by 2m and summation squared root, and this is a squared root, and which was a squared root in which we are taking in here. So I will run it here. Then I'm gonna come and run in here. Okay, all tests is pasted, and cost initial v zeros 75.2 of 0, and this is the gradient descent how we are writing it. And actually, yes, actually I guess I shouldn't read all of them, but yeah, okay, I will. In this section you will implement the gradient for parameters WB for linear regression as described in the lecture videos. The gradient descent algorithm is given in here, and parameters WB are both updated simultaneously, and where m is the number of training examples in the dataset, and you will implement a function called compute gradient which calculates this one, and this is the exercise to complete the compute gradient function to iterative over training examples, and each example compute the prediction of the model for that example. The gradient for the parameters WB for that example return the total gradient update from all the examples, and here m is the number of training examples and summation is a summation operator. Okay, if you get stuck you can check into present after the cell. Okay, let me see here, we're just writing code in here. I'm gonna click the hints in here, and I will stop recording now. I'm gonna try to fix it, then I will restart to how did I solve. Okay, let me explain what I done. And in here, if you go here, we have FVB x over I is equal to VXI plus B. So this is was, where is it? This is was first function in here, and we give it as a prediction. So I just write here the prediction, if I can find clearly. Where was it? My calls. No, that wasn't here. Yeah, okay. I take the prediction again. In here, where am I? Gradient function, yes, okay. Again, the prediction and error prediction. This is the prediction and error prediction is for the second part of it. This is taking this one minus UI for taking everything, and these are the zeros, and we are plus equaling the error xi through finding in every step. So I'm running this one. Actually, I explained it bad, but I got it. Let me run it. Maybe it's wrong. Oh, okay, it's working. And now let's gradient descent algorithm implement above our dataset. And let's doing it. And here the learning parameters using batch gradient descent. You will now find the optimal parameters of a linear regression model by using batch gradient descent. Recall batch refers to running all the examples in one iteration. You don't need to implement anything for this part, simply run the cells below. And a good way to verify that gradient descent is working correctly, look at the value of j of b and b. For decreasing with each step, assuming you have implemented the gradient and computed the cost correctly and you have a appropriate value for the learning race alpha, and should never increase and should converge to still the value by the end of the algorithm. I'm just running here. Is this working? Yeah. Now this is the algorithm about the parameters. These are the iterations. It's just running the same calls again and again and again, and we are finding the expected output will be found by gradient descent in here. And we will now use the final parameters from gradient descent to pilot the linear fit. Recall that we can get the prediction for a single example, and to calculate the predictions on the entire dataset, we can loop through all the training examples and calculate the prediction for each example. This is shown in the code block below. We're just running it and put predicted values as a linear fit. Let's check. Yeah, as I said before, going like this one, but probably we can make it less like this one. But I didn't made calculations in my head, so I'm not sure. And the final values of VB can also use to make prediction on profits. Let's predict what the profit will be areas 35k and 70k people. The model takes population for each 10k as input. Therefore, 35 can be transmitted into output models array numpy.array 3.5. Similarly, 7,000 people can be translated into the input, the model as numpy.array 77. Then if we can run this one for the 35k population, we profit things like 4.5k per month, and for the 70k people, we predict a profit for 45.3k per month. And okay, it's end of the season. Thanks for the listening. Have a good day.